Hello class, these are our notes for Calculus AB, section 5.1, the natural logarithmic function differentiation. So we are looking at natural logs today, and we are taking derivatives. So we just need to do a quick review of natural logs. So logs in general, if I write log and then I put a little number down here, that's my base. So log base 2 of 8. What we're getting at is when we write this, it means find the exponent. So this means this gives you an exponent. And it's the exponent it takes to get from the 2 to the 8. So the 2 is the base. So it's basically saying like 2 to what power is equal to 8? And that's going to be 3 because 2 to the third power equals 8. So this is the log form. Log base 2 of 8 equals 3. And then the exponent form would be 2 to the third power equals 8. So those are equivalent. So this is the log form. This is the exponent form. And then I do want to make a note here that the 2 is the base. So logs and exponents are inverses. So this should be review of Algebra 2 and Pre-Calc so far, but we need to make sure that we understand some log properties to be able to do what we want to today with our calc work. So if we write just the word log, that means base 10. If we don't write a base, it's base 10. And then natural log is, of course, base E. ln stands for natural log. So we are focusing in on natural logs today, but first just a little review of log properties. So if I write log of 1 or natural log of 1, that's going to equal 0 because anything, so it doesn't matter what my base is, e to the 0 power is going to equal 1. So because e to the 0 power equals 1. So if I wrote like log base 2 of 1, that's going to be 0. Log of 1 is going to be 0. So any log of 1 is going to be equal to 0 because anything to the 0 power equals 1. So if I write the natural log of a times b, we can break that apart with addition and write the natural log of a plus the natural log of b. If I have division, I break that apart with subtraction. So natural log a minus natural log b. If I have a natural log of something raised to a power, a raised to the n power, we bring that exponent in front. So I have n times the natural log of a. And I think this is all the log properties I can think of right now. I think this is going to be it. So we're going to just practice expanding logs now. And again, I know this is review, but we're going to be using this like in a different context. We're going to be using these properties for some of the derivatives that we're going to take. So for now, we're just like reviewing log properties basically. So if I wrote natural log of 10 ninths, I could make this natural log of 10 minus natural log of 9. And sometimes my L's and N's kind of morph together here. In the next one, this 3x plus 2 is really to the 1/2 power if it's the square root, so I could make this 1/2 times the natural log of 3x plus 2. And the last one, I have the natural log of 6x divided by 5. So remember, it's a 6 times an x and then divided by 5. So natural log of 6 plus natural log of x. So I can break apart multiplication with addition and then division with subtraction. So minus natural log 5. So hopefully this is all familiar. We spend a lot of time on this in both Algebra 2 and in Pre-Calculus. So in this last one, I have a fraction. And so when I'm looking at this, the parts that I can see are first we have a whole bunch of stuff in the numerator, a whole bunch of stuff in the denominator. So I'm going to write natural log of, and I would instantly go and write an answer. This is just kind of preliminary steps. So x squared plus 3 is all being squared minus, and then everything that's in my denominator, let's see, we have a natural log of x cubed times the square root of x squared plus 1, which is really an x squared plus 1 to the 1/2 power. In the numerator, I can take care of that exponent and bring it in front as a coefficient. So I have 2 times the natural log of x squared plus 3. And then here, it's a little bit tricky. I'm going to write the minus sign, and then I'm going to break apart this natural log because I'm multiplying. It's going to be broken apart with subtraction. So I have natural log of x to the third. And I can't tell if that's x to the third or the cube root. So I kind of think after looking at this that the 3 is kind of spaced apart from the x. I kind of think this is supposed to be a cube root. So that's what I'm going to go with. And then minus natural log of the x squared plus 1 to the 1/3 power. Oh, this multiplication here is a plus. And so what ends up happening is this minus sign is going to distribute to everything in my denominator. So I'm going to have a minus natural log of x and a minus 1/3 times the natural log of x squared plus 1. So that's what I really wanted you to get out of this, that everything in my denominator, the x cubed and the x squared plus 1, those both have minus signs. They are both in the denominator. So I know that there's a times sign between them, that just means a plus sign between those two, but a minus for everything in a denominator. So it works out that they're both a minus. So I would just go straight to an answer on this one, honestly, and I would just look at it and say, well, everything in the denominator gets a minus. And that's kind of how I remember how I look at it. Okay, so we've done a lot of this work here. Now we need to look at derivative of the natural log function. So if y equals the natural log of x, then y prime equals 1 over x. And so if I said instead of x, if I think about like the chain rule version, so if I have y equals the natural log of u, well then y prime would be 1 over u times the derivative of u, which ends up just being u prime over u. So this is the chain rule version. So the chain rule version is probably a little bit easier to use for this, but I want to make sure that I go through and kind of show you where that's coming from. So in example 3, we're just going through, we're taking a bunch of derivatives. So if I have the natural log of 2x, when I take my derivative, it's just going to be 1 divided by 2x. But then remember, chain rule, I also have to multiply by the derivative of 2x, which is just a 2. So I have 2 divided by 2x, which is just 1 over x. So instead of multiplying by my derivative, like I did here, if you use this chain rule version, it's just saying u prime over u right away. So that's what I want to do in part B. So in part B, what I would do is I have natural log of all this stuff. So the x squared plus 1 is going to go in the denominator, and in the numerator is just going to be the derivative of x squared plus 1, which is a 2x. And that's easier than writing 1 over x squared plus 1 times derivative of the inside, which is a 2x, right? And then multiplying. So I really feel like the chain rule version of this one is the one we want to use. This next one says x times the natural log of x. Well, that's product rule. So that means I have like an f and a g being multiplied. So it starts out with fg prime. So x times my derivative of natural log x, which is 1 over x, plus g, which is natural log of x, times derivative of x, which is just a 1. So I end up with 1 plus the natural log of x. So I feel like we see this a lot in math for whatever reason. On this last one, it's the natural log of x and then cubed. So my chain rule is that first I take the derivative of the outside, which is the cube part. So I'll have 3 times the natural log of x and then squared, and then times derivative of the inside, which is just 1 over x. So 3 times the natural log of x squared divided by x. So just kind of playing around with this new derivative rule. Okay, now we're going to go ahead and differentiate this one. So it's the same thing. We're still just taking a derivative. So now I'm finding f prime of x. So remember, I have that u prime over u thing. But I think I want to do something first. Looking at this, like I've got a natural log, I've got a square root. Wouldn't it be easier to just rewrite the way the natural log looks to start with? So when I have a natural log of a square root, I could just rewrite it as 1/2 times the natural log of x plus 1. So now, instead of having to do chain rule, I don't have a chain rule anymore, right? I don't have a natural log of something to a 1/2 power, where I have to take the derivative of the natural log and then the derivative of the 1/2 power. I don't have to do chain rule. I can just simply, I mean, I kind of do chain rule, right? But the derivative of x plus 1 is super, super easy. So now, when I take my derivative, I have a 1/2 in there. And when I'm looking at the natural log of x plus 1, it's just u prime over u. So my denominator is the x plus 1. My derivative of x plus 1 is just a 1. So I end up with 1 over 2 times x plus 1. So I could get the same answer by taking a derivative of this, but it's going to be a lot more work, right? I'm going to have 1 over that x plus 1 to the 1/2 power. And then I'd have to have a 1/2 in front of this guy. And then x plus 1 to the negative 1/2 power. It's just a lot more work. And then times a 1. So I could take a derivative of that, but it's going to be a lot easier if we use our log properties. So that's kind of what we want to get out of this right now, is use your log properties before you take derivatives. It will simplify the derivative that you're taking. All right, next page. They get more difficult. So now look at this one. Same thing, we have a big mess, but we've just talked about using our log properties first. So I'm going to go ahead and I'm going to break apart this logarithm. So what I can see here is in the numerator, I have an x times this stuff that's being squared. And then in my denominator, I have all this stuff to the 1/2 power, basically. So when I rewrite it, I'll have the natural log of x plus, so that's from this x right here, and then I've got this guy to the second power, so I'm going to put a 2 in front and make it natural log of x squared plus 1. Okay, that's my whole numerator taken care of. Now I want to look at the denominator. Everything in the denominator gets a minus, and because I have a square root, it's a 1/2 power, so I have a 1/2 natural log of 2x cubed minus 1. So I've rewritten the way it looks. I no longer have to do a quotient rule or a power rule because I've broken all that apart. Now I've just got to go through and take derivatives of my natural logs. So natural log x derivative is just 1 over x. The second one, I have a 2. That's going to go in my numerator. And then remember, it's like u prime over u. So the u part is everything inside my square root. The x squared plus 1, that's going to go in my denominator. And then my numerator is going to be the derivative of x squared plus 1, which is just a 2x. And then minus my next fraction, I have a 1/2. And then remember, same thing, u prime over u. So this whole thing right here is my u, that's my inside function. I'm just going to rewrite that in the denominator. And then in my numerator, I have to take the derivative of that inside part of the 2x cubed minus 1, which is just going to be a, let's see, 3 times 2 is a 6x squared. And then I would want to do a little bit of simplifying here, but not much. So 1 over x plus 4x over x squared plus 1 minus 6 divided by 2 would be 3x squared over 2x cubed minus 1. So much easier. I guess these are the derivative too. I did not label them the derivative. So much easier to take a derivative using these logarithm rules. All right, so the next one, we just keep getting a step harder and a step harder. On the next one, it just says y equal this crazy fraction. right? So I know you're thinking, how do these log rules help me? But what we can do is we can start out by taking a log on both sides. So we're going to start out, this is called logarithmic differentiation. And basically the idea behind this is for something that's really complicated, like this fraction here, by taking a log on both sides and using log rules, we can simplify the way it looks. So logarithmic differentiation, basically we're looking for a complicated fraction typically. It could just be a product rule kind of thing, but this fraction with something raised to a power, or especially product rule, like anything like that that looks like a complicated derivative, this is a good candidate. So our first step is to take a natural log on both sides. And then our second step is to use log rules to break apart, which is really expanding. And then our third step is to take a derivative. And there's kind of a fourth step too, but I think we need to get to that in a minute. So logarithmic differentiation, the first thing I want to do is I want to take a log on both sides. So instead of y, I now have natural log of y. And we're using natural log because the derivative of natural log is really easy to work with. On the other side, I would write natural log of that big fraction. Right, then on the right, what I'm going to do is use those log rules to expand, to break apart those logs so that I don't have to do some big complicated thing. So I don't have to do quotient rule, I don't have to do product rule, I might not even have to do much chain rule. So I'm going to bring so the numerator, right, is going to be 2 times the natural log of x minus 2, minus denominator is going to be a 1/2 natural log of x squared plus 1. Okay, now that I have that broken apart, I want to go ahead and take a derivative. So this is tricky because when I have a derivative on the left, I have a y. So I have to think about what happens when I'm taking a derivative implicitly. Well, when I take a derivative implicitly, I have to take my derivative of just a natural log, right? That's going to be 1 over y. But then I'd have to multiply by dy dx, or just the derivative of y. So I'm going to write it as y prime over y. I could write it with 1 over y times dy dx, but I think this is going to be easier. So y prime over y, just like I would if it was u prime over u. And then on the right hand side, I want to go through and I want to take all those derivatives as well. So this one, I've got the 2 that I need to keep there. It's just a constant. So when I have this natural log of x minus 2, remember the x minus 2, it's going to be like 1 over x minus 2 times the derivative of x minus 2, or I could just write the x minus 2 in the denominator. Derivative of x minus 2 is just a 1, so I'm going to write times a 1. Minus, the next one I have the 1/2. I'm taking the natural log of an x squared plus 1. So that means the x squared plus 1 is going to go in the denominator. So when I take a derivative of natural log, it's like 1 over the x squared plus 1. And then my numerator is the derivative of x squared plus 1. So that is going to be a chain rule. Derivative of x squared plus 1 is a 2x. So when I simplify my numerator, there's not really much to simplify. This is just going to be a 2. And this one's really just a 2x. So I'm going to go ahead and fix that right now because I'm out of space pretty much here. So we have a 2, and then the second fraction just says a 2x. So I want y prime by itself, so I need to multiply both sides by y. Well, y is this entire fraction. So if I multiply by y, right, that's what I want to do. Then I'm going to write y prime equals, and I have the fraction x minus 2 squared over square root of x squared plus 1. So I'm substituting y back in, times, and then I have 2 over x minus 2. I don't have parentheses there, so I don't need to close them. minus 2x. Actually, this could just be an x over x squared plus 1. So we could spend some time getting common denominators, putting fractions together, but we could also just leave it like this. I think it's worth it in class to maybe spend another minute on the simplifying process. So last step here was to sub y back in and simplify y prime. Or maybe isolate y prime, sub y back in, and then simplify. I guess you could write that too. So if I want to get a common denominator here, my first fraction, I need to multiply it by x squared plus 1 over x squared plus 1. The second one by x minus 2 times x minus 2. And then what would happen is I would have an x minus 2 squared over square root of x squared plus 1 times, let's see, my denominator here would be x minus 2 times x squared plus 1. And in my numerator, I would actually go through and expand. So I would have 2 times x squared, 2 times 1, and then minus x squared, and then negative times negative would be a plus 2x. So let's see. I can cross out a factor of x minus 2 with the square right here. If I have x squared plus 1 to the first power times x squared plus 1 to the 1/2 power, that's going to be a 3/2 power. So let's see, I have y prime equals, my new denominator is x squared plus 1 to the 3/2 power. Again, first power plus 1/2 power is 3/2. And then I can put those x squared terms together. And let's see, oh, I have the x minus 2 still. But then for the other one, 2x squared minus x squared is going to be an x squared plus a 2x plus a 2. All right, that looks great. So like I said, just that little bit of algebra practice. You could just totally have stopped once we had y prime by itself. Depends on the directions, but sometimes we do have to go through and simplify. So for this next one, the absolute values are there. Remember, we can only take natural logs of positives. So absolute value because we can't take a log of a negative. I can't take something positive, raise it to a power, and then get a negative. Exponents just don't work that way. So for this one, remember, if I have the natural log of u and I take a derivative, I get u prime over u. So that's what I want to do here. My inside function is cosine x. Well, derivative of cosine is negative sine x. And then u goes in the denominator, so I just rewrite that inside function, cosine x, in my denominator. So it's really weird to do all this trig stuff and just have one step. Last one, we're trying to find extrema. So if we want to do this, remember just like before, we need to take a first derivative, set it equal to 0 and undefined to find our critical numbers. We can investigate them by making a chart. So let's start out with finding our derivative. So y prime equals u prime over u. So that means the x squared plus 2x plus 3 goes in my denominator. My numerator would just be 2x plus 2, the derivative of that inside function, x squared plus 2x plus 3. And then I need to find my critical numbers. So critical numbers come from making y prime equal to 0 and also seeing where y prime is undefined. So when it's equal to 0, that means numerator equal to 0. So I would want to take 2x plus 2 and make it equal to 0, which means 2x equals negative 2 or x equals negative 1. To figure out when it's undefined, I would set my denominator equal to 0. And I can't factor this, so this is where I would grab my calculator and solve, and it turns out that there are no real roots. So if there's no real roots, I don't need to worry about this. I could also figure that out by hand. I could do the quadratic formula. The part inside the square root, the b squared minus 4ac part, would be 2 squared minus 4 times 1 times 3. So we can really quickly see how that'd be a negative. So, but again, use your calculator. Use your calculator if you can. So then I want to go ahead and make a first derivative chart. So let's go ahead and make a first derivative chart. So I'm going to write f prime of x to remind me I'm looking at my first derivative. So -1 is the only real number I'm investigating. So I want to check something smaller and something bigger. I'm going to check, what am I going to check? Like maybe a positive 10, something really big. So if I do a natural log of 10 squared plus 20 plus 3, e only to a positive power is going to make us such a big number like that. What if we have a negative 10? Does that even work? Well, if I use negative 10, I have the natural log of 100 plus 2 times negative 10. Actually, no, I'm looking at this one right here. I'm looking at this one. So with x equals 10, I get positive over positive. If I have a negative 10, I have a negative over a positive. So I'm looking at my y prime when I'm doing this chart. I almost looked at my original function. I did look at it and then I fixed it. So this would be a negative. So again, positive for this one because 2 times 10 plus 2 divided by 10 squared plus 2 times 10 plus 3 is a positive. The other one, 2 times negative 10 plus 2, that makes a negative. Denominator is still going to be positive though, right? Because negative 10 squared is such a big number, it doesn't matter that 2 times negative 10 is a negative. That's going to be negative. So now that I know it's a minimum, I have found a relative minimum. I'm pretty happy with that. But I got to figure out, I only know where it is. I don't know what it is. So I do need to find f of -1. So let's go ahead and have that be our last step here. I don't know why that didn't erase very well. There we go. So let's go ahead and find f of -1. So that's going to be, let's see, natural log of -1 squared plus 2 times -1 plus 3. So natural log of 1 minus 2 plus 3, which is the natural log of 2. I could figure that out, but remember in math we don't really care. We like numbers like this. So we have a relative minimum of natural log 2 at x equals -1. So our minimum is that natural log 2. So don't just write an ordered pair. Be really careful about that. That's what your textbook does. An AP will just not accept that as an answer. So main ideas for today. If I go back to the top here, my main ideas for today are, first of all, just remembering our log properties, right? So that's one thing. Remember our log properties. And my pen is all of a sudden not working. I guess it's working. So log properties. And then this idea that we can use log properties to help us out when we're differentiating. So like on example 4 here, I went ahead and used my log properties to expand and then took a derivative, right? And we really saw that on the example after that, on example 5, this idea of logarithmic differentiation. So that's one of our ideas as well, is to differentiate. We really want to use that logarithmic differentiation, make our lives easier. It's tricky because on anything, they're not going to cancel. I think that I have accidentally closed my session down. So I'm going to go ahead and stop the Screencastify right now. As always, if you have questions, please make sure you ask them in class.